when you're having fun. So hopefully the audience is enjoying these presentations as much as I am. The penultimate presentation for this virtual pipeline summit is entitled Application of Distributed Fibre Optic Sensing for Pipeline Integrity and Security. Dr. Alasdair Murray, a senior data analyst with OptaSense in the UK, will present an overview of the Rayleigh backscatter method and briefly detail how OptaSense can provide in-field verification of performance. Alasdair holds a master's degree in physics from the University of Exeter in 2010 and obtained a PhD with the Electromagnetic and Acoustic Materials group of the same university in 2014. His thesis was on the subject of the airborne and underwater response of acoustic structures. In the same year, Alasdair joined Kinetic to work with the Acoustic Stealth Materials Department. This presentation has been pre-recorded, and Alasdair will join us at the end to answer your questions.
Hello, my name is Alasdair Murray and I'm a senior analyst with OptaSense. This talk is about the application of distributed fibre optic sensing for pipeline integrity and security. OptaSense is a leader in fibre optic sensing, with expertise covering the design and development of fundamental system components through to the provision of training and support networks. Our systems have been deployed all over the world and presently monitor more than 25,000 kilometers of asset. So how does fibre optic sensing work? At its core, it relies on sending light down an optical fibre. As the light propagates, it interacts with microscopic defects in the fibre, a tiny fraction of which is scattered back towards the interrogator unit, where it can be detected. External events, such as physical activity, strain, and temperature changes, cause variations in the scattered signal. These variations can be exploited to detect and interpret events in real time. There are three mechanisms that can be used for fibre optic sensing: Rayleigh, Brillouin, and Raman scattering. The OptaSense system utilizes Rayleigh scattering, which is generally considered to be an acoustic sensor. However, recent technological advances are allowing Rayleigh-based sensors to provide strain and temperature measurement capability as well. With this technology, there are qualitative and quantitative variations. The qualitative or intensity-based system can show us that something is happening to a fibre, while more advanced quantitative systems allow us to measure what is happening to the fibre. In the slide images, we can see the difference between the effect of an impulse-like event on each of these systems. In the first case, channels in the vicinity of the impulse show an effect, but there is no relationship between the responses. While on the quantitative system, the response of each channel is coherent, and the amplitude provides a measure of the change in the optical path length. This allows far more information to be extracted from the data. OptaSense can provide both qualitative and quantitative solutions, with the choice being recommended according to the requirements of the system. For many scenarios, a qualitative system provides the necessary capability. For instance, a person walking parallel to the fibre will manifest as a periodic series of impulses that move along the fibre at a slow pace. This is true of both qualitative and quantitative systems. Heuristic algorithms can be used to detect and classify these impulses as walking, and it makes little difference as to how the impulses were detected. Quantitative systems can potentially provide more detail, such as the bearing of the walker and the offset from the fibre. For certain applications, such as fracture monitoring, where the interaction and propagation of waves in the ground are important, a quantitative system is essential. OptaSense has a fleet of detectors to allow us to provide the right detector for the job. Our standard workhorse is the OLA 2.1 unit, which is suitable for most pipeline and intrusion applications. Our other detectors can all provide quantitative data, with the latest Plexus unit providing quantitative data over the same range as the OLA 2.1. The loss of integrity along a pipeline can have a significant impact on the environment, on reputations, and on finances. Fibre optic sensing can be employed to provide leak detection, third-party intrusion, and scraper tracking, all from a single platform. Let us first consider leak detection. During a leak, there are a number of physical phenomena that can be used for identification. Our four-mode leak detection system continuously monitors for four such indicators. These are the negative pressure pulse, orifice noise, strain, and temperature changes. At the instant a pipeline loses integrity, a rapid pressure drop occurs. This generates a negative pressure pulse in the system and manifests as a signal propagating along the pipeline at the speed of sound in the fluid. As the signal propagates out in both directions along the pipe, it provides us with the characteristic V-shape that can be seen in the image. Orifice noise arises as fluid is ejected from the pipeline and vibrates the surrounding environment. This appears as significant amplification in the spectral content. The force of fluid being ejected from the pipeline can cause the surrounding ground to shift. This is particularly noticeable in compressed gas pipelines where the fluid undergoes a rapid expansion into the surrounding area. Where the fluid is at a different temperature to the fibre or undergoes rapid cooling as it expands, thermal changes will permeate towards the fibre, causing detectable changes. The plot shows the effect of a leak measured on a quantitative system, where the strain and temperature effects are easier to visualize. The vertical dashed line marks the instant at which the leak begins, and in the first few minutes afterwards, a significant peak arises as the ground strains and relaxes. The latter change, observed as a downward slope over several minutes, arises as the temperature of the fibre is affected. Over the years, we have engaged in numerous trials to understand and develop our leak detection system. I want to briefly mention two of the larger trials we have undertaken, and which are the most representative trials performed to date. In 2017, at SINTEF in Norway, we undertook leak testing on their above-ground flow loop. Tests were performed for liquid, gas, and mixed-phase leaks, covering a total of 540 different scenarios. The fibre optic cable was taped onto the flow loop, which was found to be an effective means of reducing environmental noise on this exposed pipeline. In 2019, we went to EITEP in Brazil, where we had installed a bespoke test spool on their 2-kilometre-long buried flow loop. Again, a series of tests were undertaken with liquid, gas, and mixed-phase products under a variety of conditions. Further details from both of these trials are available by inquiry. On the next slide, I will share with you one of the EITEP leak tests in action. As the left-hand waterfall scrolls, we will see a negative pressure pulse occurring. There. The effect is rapid and can now be seen as a faint horizontal line scrolling downwards. As fluid continues to leak out of the pipeline, the orifice noise produces a red vertical streak on the waterfall, and there is an amplification of the spectral content as observed in the central display. Shortly after the initial pulse, an alert icon appears on the map display, indicating the location of the leak. This data is from a leak at a rate of approximately 125 litres per minute. As the orifice noise continues for sufficient time, the system produces a further detection that is fused with the NPP and upgrades the alert. From our extensive trials of the leak detection system, we have considerable confidence in it. The graph in the bottom left indicates the response of each of the leak detectors compared against conventional CPM systems, and the table in the top right shows the performance that we expect from the system. For the smallest leaks, the only indicator may be a negative pressure pulse, at the instant pipeline integrity is lost. As such, we consider this to be the most valuable signal, and it is run independently. With this, we can provide near instantaneous detection with the characteristic V-shape acting as an arrow pointing directly to the source. The stated 1-minute response time takes into account the amount of time required for a trained operator to acknowledge, investigate, and confirm the alert. For larger leaks, the NPP detector is augmented with our fused leak approach, which builds confidence by combining detections from each of the different leak modes. The question, of course, arises over how we can validate system performance in the field. To this end, we have developed several methods. Burst-its testing allows us to generate negative pressure pulses at convenient access valves. Ground fluid injection probe allows simulation of orifice noise, strain, and temperature effects on the fibre by injecting fluid at high velocity into the ground. Our leak simulation unit allows us to replay signals obtained from leak tests onto any system at suitable access points. During our trials at EITEP, we simultaneously recorded the leaks on both qualitative and quantitative systems. The quantitative recording allows us to replicate the effect of the leak on the fibre. A client recently undertook field verification of their own using this burst disk methodology on a short exposed section of a buried pipeline. OptaSense provided remote support in order to record the testing and to address any issues. As it happens, during the first couple of tests, only the one side of the negative pressure pulse was observed, which we determined to have resulted from a large air pocket that was preventing the signal propagation. The client was able to dislodge this air pocket, allowing the testing to be completed successfully. In the image, the white arrow indicates the origin of the leak, with a strong signal propagating for many kilometers along the pipeline. A negative pressure pulse is time-stamped around 2 seconds after the event, and shortly afterwards the system detected orifice noise, which fused with the earlier detection. We can also use fibre optic sensing to track the location of scrapers through a pipeline. As the scraper moves through the system, the interaction with the sidewalls and butt welds creates a series of moving pressure waves throughout the pipeline. These can be seen on the waterfall display to the top right as they're being created. Detection of these pressure waves allows for the real-time tracking and locating of the scraper throughout the system. The image on the bottom left shows a waterfall of a scraper running through 33 kilometers of pipeline. Over the course of 9 hours, the system detected and formed a single continuous track. As also can be seen in the waterfall, scrapers can create considerable signal, and the ability to track them continuously allows the suppression of nuisance alerts that might otherwise arise. Let us now turn to third-party intrusion. There are a number of activities that can be categorized as being of interest. The presence of digging and drilling in the vicinity of a pipeline are significant events, while vehicle movements and the presence of walkers may be of concern. Each of these activities has a fingerprint that allows swift, real-time identification and locating of the events. For example, digging consists of semi-regular impulses, while mechanical digging adds tonal features from the engine, and the impulses are likely to be much larger. Of course, there are some shared characteristics between different activities that has the potential to lead to nuisance alerts. And so while the pipeline operator may not care about the movement of trains, for example, the system can classify and track these events in order to filter out nuisance alerts that might otherwise be generated. Let us consider an activity that can be of significant concern: hot tapping. In the build-up to a hot tap event, there are likely to be several activities in the vicinity of the pipeline, such as personnel and vehicle movements, digging and drilling. As these alerts are observed by an operator, a response can hopefully be raised prior to the pipeline being breached. However, in the event that the pipeline is breached, then we can observe negative pressure pulses, as in the lower left image, and potentially the other leak modes. A Latin American client was recently showing product loss on their mass balance system. Using the fibre optic detection system installed, they were able to identify the location and apprehend the thieves at 2 separate locations. Before finishing up, I want to briefly overview the architecture of a typical system. On the screen, we can see a schematic of a typical installation. The blue horizontal line represents the monitored asset, with a number of physical locations along the asset to house one or more optical interrogator units. Each location can house detectors looking in opposite directions to provide 100 kilometers of fibre optic coverage from a single location. A secondary network, indicated by the red line, provides a backbone for the communication between all the hardware and allows remote monitoring from one or more locations. From this secondary network, we can also provide external outputs and connectivity. Regarding the installation of the fibre, on a buried pipeline, it can be directly buried or installed in conduit. For leak detection purposes, the proximity is more important than the position, and we specify that the fibre should be within ½ meter of the pipeline. This is not a hard limit, but as the fibre gets further away, there will be a reduction in sensitivity. For TPI classification, the proximity to the surface is the more important factor. On an exposed pipeline, the fibre is typically taped and strapped onto the pipeline itself to mitigate against the effects of environmental noise. The OptaSense system has been deployed all across the world, and here we mention just a small number of these installations. On TANAP, we're providing leak detection and intrusion detection for a little over 1,800 kilometers of pipe in a single installation. A South American installation employs the system along 530 kilometers of an iron ore slurry line. We're currently in the process of completing phase 3 of the EPIC midstream line in the Permian Basin. These are just a small selection of the larger installations currently employing fibre optic monitoring from OptaSense. To summarize, The OptaSense pipeline integrity and monitoring system provides a suite of pipeline monitoring from a single remote platform. Leak detection, construction, hot tapping, and sabotage can all be detected and classified using a suite of advanced algorithms. Large-scale trials have demonstrated the ability of our 4-mode leak detection system to rapidly detect leaks down to 15 litres per minute. Scrapers can be tracked continuously throughout a monitored pipeline in real time, providing real-time speed and location data, along with indicators of pipeline condition. Thank you for listening, and if you have any questions, please don't hesitate to get in contact.
And now we welcome Dr. Murray after that video. Hi, Alasdair, how are you?
Hi there, Danny. I'm good, thank you. Sorry about the signal seems to be a bit poor.
No problem, I can hear you just great. And that video was fantastic, so maybe a good plan to pre-record in that case. So we've had many questions coming in for all our presenters this afternoon, so thank you very much to the audience for engaging. I'm sorry that we haven't had time to answer all of them, but they will be forwarded to the presenters and they'll be able to follow up with you afterwards. So Alasdair, maybe we could start with an anonymous question that's come in. What is the smallest leak that you're able to detect?
Okay, so this is a good question. For the liquid leak, the smallest specified rate at which we can detect is 15 litres per minute. But during the testing we performed out at CT Duke, the smallest that we actually successfully detected on was 1.5 litre per minute leak. But as we had so few tests at this rate, we didn't feel confident that we could put it out as a specification. So that was for liquid leak, and for gas leak, using our testing, we specified 2,000 litres per minute. The biggest difficulty with performing smaller gas leak tests is that the rate at which the pressure can drop is limited by the rate at which the gas can leave the pipeline. It's the sonic condition, and so the rate at which the pressure drops is lower than for a liquid leak. I hope that answers it.
Yes, I think so. Thanks for that. Another anonymous question is, can you rely on NPP if it's an old leak, which is getting bigger?
Okay, yes. So as I said in the slides, the NPP is the detector that we rely on the most because it occurs instantaneously at the moment of the leak. But if we're talking about a very, very small leak that perhaps doesn't generate an NPP, or if the system happened to miss it, then what happens later on? And as I stated, we do have the orifice noise, strain, and temperature change detectors, which augment the NPP detector. And so as the leak grows, these will become more useful. However, another point to that is, particularly for liquid leaks, if there is any glugging going on as the liquid exits the system, it will generate further pressure pulses, which will exhibit as in a similar manner to the negative pressure pulse. And so there are further opportunities for detection.
Of course. We have a couple of people asking whether this can be used offshore.
So we do have some trials going on using fibre optics offshore. There's obviously a question of how you install the fibre relative to the pipeline, but that's something that is probably best followed up with as offline, as it's not really my area of expertise.
No problem. Veronica Iglesias asks, what type of fibre optic cable do you use for this project?
So our systems generally rely on a standard single mode fibre optic cable. Multi-mode causes problems, but there is work going on to look at using specialist fibres to allow detection at greater ranges, or to enhance the sensitivity of the system. But typically it can be installed on any single mode telecoms fibre.
Okay, Alasdair, thank you. Just one final question before I let you go. From Maria Clara Duenas. She's asking if you have had any experience in Colombia.
Personally, I haven't had any experience in Colombia, and I don't know, again, it would have to be taken up offline whether we have any sales opportunity, any clients in Colombia. Unfortunately, I don't keep track of all of the installations.
No problem. Perfect. Thank you very much for that, Alasdair. Sorry that we haven't seen a reappearance of your cat today from the practice earlier this week.
I think that was probably a good thing.
Thanks again, Alasdair.